Oh, I am. All right. How's your laptop? Whoops. Volume. Alrighty, welcome back to operating systems. So today we get to have some practice with our processes. We know how to create processes. We know how to wait for them. Kind of know how to communicate between them. So today we'll be doing more practice with this. I will introduce to you one new system call that will actually give us another way to have IPC or inter-process communication. So first off, based off some of your feedback, some of you want to write an operating system as part of this course. So not where this course is aimed at, but if you are interested, the goal of this course is we kind of hang around at that system call layer. We're supposed to, figure out what goes on in the kernel without actually writing kernel code. If you want to actually write kernel code or go on to grad courses or something like that, there's this little MIT kernel that is a full Unix operating system, so a kernel plus a bunch of programs that by the end of this course you should at least be able to read. Even if you don't get some of the implementation details, we can kind of figure it out. So it's a re-implementation of like a very old version of Unix, which everything is based off, so it would have you implement fork and all of those things. So we can read part of it, so we could actually read init from their code and actually understand what it is doing. So their init, remember init responsible for creating every other process on the machine and also being kind of like the orphanage that would wait on any child process. So here is their whole version of init. So it's just four semicolon, semicolon, that's just while true in infinite loop. So while infinite loop, it says print starting sh, so sh is your shell, what you type into. It forks, so it creates a new process. And here it checks, well, if there's not an error. If there is an error, then it just exits from init and something horrible has happened, so it just stops the whole operating system. Then here, if PID equals 0, is that the child or the parent? Well, that's the child, so the child process, the newly created process that it made, execs, so that's a shorthand for exec VE that we saw. So it runs another program called sh, and well, if it is successful, it doesn't reach this line. If it reaches this line, then it means there is a problem and it failed, and then it also just dies. Other than that, it just creates a sh process, and then it has another inner infinite loop that just calls wait over and over again. So it's just while true wait. So this is it being that orphanage and cleaning up any zombie children it gets, which would be very weird in any other context. But this, of course, that's exactly the technical term for it. So it cleans them up, and then if wait returns the PID of the process it created, it means the user exited from the shell, and what they do is just do a break and restart the loop and just restart another shell. So if you run this, it would just, even if you exit out of the shell using Control-C or Control-D or whatever, it would just restart the shell whenever it's done. Then other than that, if it gets a process ID less than, that's an error, it exits. Otherwise, it was just an orphan process that it adopted that was a zombie and it cleaned up, so it doesn't really care about its exit code or anything like that, just does nothing. So we all understand it's init. That's the entire init. So just while true, launch the shell. If someone closes it, relaunch it. Otherwise, just accept the zombie children or orphans. All right, cool. So a little bit of background and more me yammering at you before we get into the fun stuff. So because, I don't know, we're talking about operating systems, I have to go back like 50 years. Has anyone ever heard of DOS? Probably not. All right, really old operating system that was an example of something called uniprogramming. So that meant the operating system only ran a single process at a time, which would be very, very lame right now. So that means you can only do one thing at once. So only one core, one process at a time. You can't run two processes in parallel or concurrently. One process running at a time, no ifs, ands, or buts about it. Pretty lame. So most things now, all things now, are multiprogramming. So your operating system lets you have multiple processes that are all running at the same time, or it's juggling a bunch of them. So that's why everyone's able to run hundreds of processes on their machine at any given time. So modern operating systems, the whole goal of them is to run everything in parallel or concurrently, just depending on your hardware. So if you have, I don't know, 8 CPU cores, it tries to keep all of them active doing stuff. Otherwise, you would have a pretty bad operating system and you would probably install another one. So we have to talk a bit about some mechanics. So the scheduler, that is the software in the kernel, or the name for the specific type of software in the kernel that decides when to switch which process is currently running. So remember, to create a process, the operating system has to at least load it into memory, and then it goes into that waiting or ready state whenever it's able to run. And then the scheduler, which we will figure out later, that is the code that figures out what process gets to run. So before we talk about which process we pick to run, we'll just go over the mechanics of how we switch between different processes running. So the core scheduling loop, or how you deal with processes in the kernel, is they have a loop that kind of looks like this. If I know which processes I want to switch between, how I switch it is I pause the currently running process. So I take the CPU away from it. It can't execute anymore. I save its state so I can restore it later. So I'd have to at least save its current register values. And then I get the next process to run from the scheduler. And then in order to run that process, I restore its registers from whenever it was kind of put on the shelf. And then I give the CPU to that process, and it can go ahead and run until I do this again and pick a new process to run. So processes, that switching between them, there's also another thing we can do. We can let processes kind of schedule themselves or have the operating system maintain control. So there is a thing called cooperative multitasking, where in order to give up CPU, you have to use a system call and tell the operating system, okay, you can pause me and run some other process. You kind of opt into it. So in this system, if I want to hog the CPU, I just don't do that system call. I get 100% of the CPU until I'm done. I can just be a big jerk. So that's not how most operating systems are, because you can't trust anyone's processes or that anyone wrote anything correctly. So most operating systems now are examples of true multitasking. So the operating system maintains control and it pauses processes. You don't get a say whether or not you get paused. So that is how your kernel actually works. So for true multitasking, you have some options in order to maintain control. You can just give processes set time slices, so they just get 100 milliseconds, and then whenever they're done, you get control back. Or you can the kernel can set its own interrupts so that it gets interrupted whenever it wants, and then it gets control back, and then it can tell the current process to just stop running. So those are two ways to maintain control at the kernel level. Also, the mechanic of switching processes, like saving the state and restoring to another, that has a specific name, and it is called context switching. So at minimum, in order to save all the state and to restore the state of another process, I have to save all the current registers. You can imagine the implementation details are slightly tricky. So you have to save all the values using the same CPU that you are using to save them. So like when you run instructions, you will also be changing registers, but you're trying to save the registers whatever they currently are without changing them, which is, as you might imagine from your assembly course, kind of tricky. So thankfully, there's hardware support to help you save the state of the registers. Sometimes you might want to save everything though, because whenever you context switch between processes, you're not actually doing any useful work. You as a user, you only care about your processes running, so anything else the system's doing, you don't care about. We call that overhead. It's essentially wasted time wasted towards other things that aren't running your programs that you actually care about. So context switching, pure overhead, you want to be as fast as possible. If your operating system spent like half its time just saving values and switching between processes, that means, It would be twice as slow as any other operating system that's written by a normal person, and you probably just would never use it. So you want the overhead of context switching to be as low as possible. Sometimes you can use a combination of hardware and software to save as little as possible. For example, if your process doesn't use floating point registers or doesn't do floating point operations at all, there's special floating point registers on your CPU, so if the kernel's smart enough to know that you don't use them, it might just not save them as part of switching processes, and then doesn't have to bother saving them, saves it a bit of time in order to get this down to be as fast as possible. All right, on to the fun stuff now. So we get a new system call today. It is called pipe. How pipe works with file descriptors. So it takes as an argument an array of 2 integers, and it will assign values to them, assuming that this pipe system call is successful. So pipe returns a number. It's 0 if it's successful, -1 on failure, and then it sets error no, all that stuff we know from before. And it will actually set the elements of this array for you. And how it sets them is it creates a pipe. What a pipe is basically it is like a region of memory that the kernel controls that you can actually use the file descriptors to send data to and get data from. And you do that through the file descriptors. So at index 0 is the read end of the pipe. So I'm allowed to use the read system call using that file descriptors to get data out of the pipe. And if I want to put data into the pipe, I use the file descriptor at index 1, and that is the right end of the pipe. So I use the write system call to put data into that pipe. So the pipe you can think of as a kernel-managed buffer, a region of memory, whatever you want. But the way it works is that any data you write to it, you can read from the other end of the pipe. It's like a one-way communication channel. So, yep.
Can we set which file descriptors it goes to, or does it have to be the one that the pipe assigned themselves?
So the question is, can I
reset the value of 0 or 1 index?
Yeah, so can I force the file descriptor numbers it gives me? And the answer to that is no. It just returns new unused file descriptors for you. So we don't have a choice what we get back through this. Yep. So the question is, if I give it an array that's bigger than this, will it be okay? Yeah, you can give it a larger array if you want. It's just going to write the first 2 elements of that. Yeah, but you should typically only use an array of size 2 so it fills up, and then it describes one pipe, so it's a bit easier to organize like that. But it's C. You can do whatever silly things you want. Okay, so let's have, here's a fun quick aside. So remember that while true fork that killed my computer? So here's a fun way to do that you can send to your first years and essentially trick them into running that without actually writing C code. So if you've used your shell and you use an ampersand at the end of your command, your shell starts that process, it just forks, creates that process and returns immediately. So whenever it finishes, it'll clean up and tell you whenever it exits. So if I do sleep 1, I get it would return immediately. I could type other commands back into my terminal, and it will tell me whenever it ends. So fun thing I can do, we also saw the pipe character to create a pipe between 2 processes. So in order to write while true fork in bash, I can actually write this, and if you execute this, that will fork bomb you. It will do while true fork. And how it works is in bash, you can define a function called colon. That is a perfectly valid name. Don't ask me why. But in order to kind of fool a first year into running this, they won't know what this means. This defines a function called colon. And in the body of it, kind of like C syntax, it calls colon, which would create another process, pipes it to another colon, and throws it in the background. So every time it calls colon, it creates two other colons, kind of glues them together and runs them. And then this just ends the line, and then this colon calls colon. So it starts off the recursive call, and then that's a fork bomb. So don't run this on the lab machines, but if you want to screw with, I don't know why this course is like just screwing with first years, but you can tell them to run that. That will do while true fork. Otherwise, don't run that. I don't really know why I showed that to you. I probably shouldn't tell you these things, but there it is. All right, let's do the example. So let's go to a code. So what we are going to write today is we are going to use a pipe to communicate between two processes that we create. So I'm going to use a bunch of system calls, so I'm going to write a little helper function called check that pretty much all these system call wrappers will return -1 if there's an error and set error no. So in order to save myself from writing, I write this check function that checks, hey, if the return value is not equal to -1, do nothing, there's no error. Otherwise, save error no because this p-error function may set it. Use p-error, print the message, and then exit the process. So it just ends the process. If there's an error, should give me an error message anytime. So that is just my helper function. Aside from that, I don't have anything else. So what I'm going to do is I'm going to create a pipe first off. So say, I'll give it a name. I'm running process 100. And by default, here, I'll write out a bigger one. So by default, the convention is that you will have 3 file descriptors open whenever you start a process. So file descriptor 0 is standard in, file descriptor 1 is standard out, file descriptor 2 is standard error. So those are your 3 file descriptors you always assume that are open whenever your process starts running. And then what we do is we declare a int array of 2 ints called fds because I am not very creative at naming things, and then we call pipe. So this system call creates a new pipe and then sets the file descriptors. Whoops. So it would return new file descriptors and write them to the array. So likely, we know that it would probably use the next 2 unused file descriptors. So we'd get file descriptor 3 equal to fds 0, and that is the read end of pipe. So sometimes it's good to figure out, what file descriptors are pointing to what. Now we have fd4, that would be equal to fds at 0, which is the right end of the pipe. So assuming it's successful, I can use these file descriptors to either put data into the pipe or read data from the pipe. Yep. The check function, the check function just checks if that value is -1 and then prints an error. So I just use it for my error checking code so that if it makes it through the check, there's no error, my program is working as I expect. So it's just a little helper function for me. All right, everyone okay with that? All right, so next thing I do is fork. So I'm creating a new process, and then the only difference between them is going to be the return value of fork. So let's say I create, I don't know, process 100. That's the one that called fork. So let's say we created process 101. In process 101, what would the value of PID be? 0. So PID is equal to 0. And because they are exact copies of each other at the time of the fork, process 101 will have all of those file descriptors open. It will have all those variables and everything like that. So it will have FD3, FD4 that point to the read and write end of the pipe, and same with process 100. The only difference is it would get back 101 as that PID. And then it would have FD3 and FD4 open. And remember, file descriptors are like pointers kind of managed by the kernel. So process 100 has file descriptor 3, and file descriptor 3 is pointing to the read end of the pipe. Process 101 also has file descriptor 3 pointing to the same thing. Yeah?
If we have like the pipe after the fork, we will not have all the same thing open, right? Same file descriptor open, right?
Yeah, so the question is, if I have this in a different order, what will happen? So if I do this. So if I do this and I fork first, well, they're exact copies at the time of the fork. It didn't really do anything, it just started executing main. And then each process would independently call pipe, which would create a different pipe in each process. So they would get probably the same file descriptors, 3 and 4, but here, instead of this, oops, in one process, oops, in one process, it would point to like the read end of pipe 1 and the write end of pipe 1, and because they're independent after the fork, and it calls pipe after the fork, the other process, let's say process 101, it would be pointing to a completely different pipe. So there'd be like 2 different pipes, pipe 1 and pipe 2. So because it's after, they're different pipes. So it'd be slightly useless. So we're taking advantage of fork and the file descriptors pointing to files. So if we create the pipe before we fork, they share, right? That's the only way both processes can get a file descriptor pointing to the read and write end of the pipe. So we're taking advantage of fork in order to actually point to the same pipe so we can actually send data between the different processes. All right, we okay with that? All right, let's write some child code first. That sounded weird. All right, so if PID is equal to 0, that means I'm the newly created process, right? So how I'm going to set it up is I want the child to write data, and I want the child to actually read the data. So the parent writes data, the child reads data, just to show that, hey, we're actually communicating across processes. So here, first thing I want to do, since I'm doing a read system call, I need just a bunch of memory set aside. So I'll create an array of characters called buffer, give it that magical size. We don't know why yet, but we will learn later. And then I just want to do the read system call. So I am reading data. I can look up for the read end of the pipe, so that is FD0. So if there's any data in the pipe, I should be able to read it, give it the buffer, size of buffer. And of course, I want to check the return values and everything. So bytes read, I can just check, make sure I don't have any errors or anything like that, and I would fail from the read. So all I want to do is read from the pipe. All right, this will be a little bit of magic, so I'll write child read. All right, so I could write something like this. That's probably what you would read, but if you're doing like a read system call, doesn't mean it's going to be null terminated at all. So I might just get a whole, like I know how many bytes I get back. I'm not guaranteed that it's not going to be null terminated at all. So you've seen %s, right? Everyone's seen that before? Has anyone ever seen this? So, some of us. So what that will do is take an additional argument, and it will only print that number of characters. It doesn't care if it's null terminated at all. Essentially just kind of truncates it. If it does happen to be null terminated. So this will just use it as a string, but only go up to bytes read characters. So even if I don't have a null terminated string, I'm fine. So some of you probably ran into this with lab 1 because it wasn't null terminated. So, all right, everyone okay with that code? So that is my child process. It's just reading. Hopefully it gets some information from somewhere. So if I run this, what will happen? Nothing. Kind of. So let's run it. So if I do run it, it does look like nothing's happening. Makes sense, right? My process 101, which is like the original process that's running, well, it just creates a child, and then, well, PID is greater than 0, so it just exits, so it doesn't do anything. And it dies, it terminates, I can use my terminal again. Yeah?
Wait, isn't it block at red?
Yeah, so, yeah, here's my question to you. What happened to my poor child?
It got blocked at red.
Yeah, my child was calling read, and that's a blocking system call, so it's waiting for data. Then I died, and what is the state of my child whenever I die? Like right at the point I die. Yeah, I'm an orphan, or I'm not an orphan. They're an orphan. So they get reparented somewhere, and are they a zombie? No, because there might still be doing this read. So we actually don't know. It might got reparented and then maybe read returned 0 to like indicate end of file or something like that. And then it terminated and it was a zombie and then it got cleaned up by the good old subreaper. We don't actually know. Anyone want to tell me what command I would run if I want to see if my child is still running? Yeah.
We can check if it has a parent.
We can check if it has a parent, so all processes do have parents. How do I check its existence? Remember, we used PID of before, so I could do PID of pipes, and it will return me any process that is named pipes. So that was my poor child that I orphaned. It has not quit yet. It's still running, but it's doing read. You might think that like, hey, this is the only process that can actually use the right end of the pipe and might actually give it data. So it's not going to do anything. It's useless. Why didn't it return 0 and it's stuck there forever? So like it's not going to terminate in this case. How would I get rid of it? How would I force it to terminate? Kill, yeah, violence. We want to force it to quit. So I know that it's useless, so I can just kill it. So kill it, I cleaned it up, it's gone. It terminated, and then the subreaper called wait on it and cleaned it all up. So the reason that happened, if you thought that like read should just return 0 because it's not possible for any data to go into the pipe, you would be accurate, but not quite. So in that child process, and this will be a good hint for lab 2 because you may run into this where like your process sticks around for a long time even though it shouldn't, and you will probably take about, if you do manage to debug it, you'll take about 4 hours. So this, if you pay attention and understand this, you will save yourself 4 hours, or if you just listen to my advice, you'll save yourself 4 hours. So my advice to you is that if your process is done using a file descriptor, you should close it. So the reason why read does not return 0 like end of file is because even though it's unlikely, this child process still has the right end of the pipe open, and it is theoretically possible, even though it is currently blocked doing a read, that it could write to the right end of the pipe and fill it up with data, and then it could write to itself. So you might be like, oh, that's weird. How could it do that? The answer to that is it might get a signal, right? In the signal handler, it could write to the right end of the pipe and give data to itself. It would be kind of silly, but it's possible. So in order to make sure that our child actually gets nothing, and we see it actually print nothing, trust me, listen to this. Close your file descriptors as soon as you know you're not going to use them. So in my child process, I'm only reading from the read end of the pipe. I'm just getting data. I'm not going to use the write end of the pipe. So I should immediately close it. I should just immediately close it. So, and we'll check for errors. So I should immediately close the write end of the pipe because I'm not going to use them. And now, because we did that, whoops, compile. So now because we did that, whenever we run our program now, we actually get output from our child. So we get output from our child now because, well, whenever the parent dies and it's done executing, as part of that, it will close all of its file descriptors. So it will close the read end and the write end of the pipe. And then the child would run, maybe, or maybe it runs in a different order. But eventually the child would close the right end of the pipe, and now there is no process running on my machine that has access to the right end of the pipe. And now your kernel can now successfully deduce that it is not possible for any data to go into the pipe, and it can actually return 0 from read, indicating end of file or indicating that it's not possible to get any data. So now, because I closed the right end of the pipe, I'm the only process with it. Read returns 0, not possible to get any data, so I just return child read and then bytes read is 0. I don't print anything, I'm all good. So everyone okay with that? Yeah?
Sorry, so you're saying that the return happens when nothing can write to the pipe anymore?
Yeah, so read will return 0. Typically, that you can think of it as end of file, but more generically, read returning 0 means no new data possible. And so if no process has a right end of the pipe open, there's no other way to get data into it, right? Yeah.
How exactly does like the pipe work? So like say if multiple things are being written, would the child get every single new message?
Yeah, so the question is, if I have a pipe and I write like a bunch of times to it, will the child get all the messages? And the answer to that is yeah. Yep. So yeah, so everyone okay with the child side for now? We'll do the parent side. So we'll see that we actually successfully send a message to it. Yeah.
All right, so quick question, right? Say if we would have closed the right end of the file descriptor so no more input could go over to the read end, right?
Yep.
And we call the read.
Mm-hmm.
Since read is non-blocking, it doesn't stop reading. There's no like
Read's
it doesn't stop at null character, right?
No, read's blocking.
Okay. So read doesn't stop until read doesn't like care about null characters, right? How you said earlier?
Yeah, read will return a null character if it read one. It will return. It will return whatever.
But like if we would have cut off the input, it would stop wherever like no more data is being written to it. Or?
Yes. Well, in this case, I only do one read system call. So I might read some data or I might get 0 out of it.
Okay.
We can change the code a bit if we want. So here, let's just write it in a loop. So while bytes read is greater than 0, I think that lines up. So let's do this over and over again. Just read from it. Same idea, it doesn't matter. Just read all the information until it eventually gets 0, like end of file, no more possible input. Doesn't matter. If it reads a null, like if it reads a null, it'll just write a null byte to the buffer. Doesn't care, right? So that's why I use this here, because it's not guaranteed to. All right, everyone okay to do the parent side? No, that was not a question. Okay, so else. Whoops, wrong index. else. So I'm the parent. So, oh, also, remember my advice to you was to close the file descriptors as soon as you're done using them? Should I do anything else in that if block?
Oh, close file descriptor.
Yeah, close FDs at 0. So in this case, you could argue that it doesn't matter because, well, if it exits out of the loop, it's going to just return, exit the process, and then all the file descriptors get closed. You would be correct, but if you change your program and you forget and it's still open, bad things might happen. So just heed my advice, and it should be written like that. So as soon as you're done using it, close the file descriptors. If there's anything you take away from this lecture that will save you hours upon hours upon hours of time, do that. All right, let's write the child. So const car, I'll call it string. I don't know why I'm Texan today. I don't know. I'll just say howdy child. And then say, let's get its length because we need to know how many bytes to write to it. And then in order to give it data, I can just do write fd 0 char length. So this one will not write the null byte because I just asked for the string length, not including the null byte, and just write to it. If I wanted to, I could, but I don't want to. Int bytes written, and then just check bytes. Do some error checking. Everyone loves error checking. All right, now if I run this, assuming everything works, it shouldn't matter what order they execute in. If the child executes first, it will just block on the read waiting for data. And if the parent hasn't executed yet, it still has the right end of the pipe open, so it'll block until there's some data. Then the parent executes, creates a string, does all that, and then writes it. So it writes it to the right end of the pipe, and then hopefully the child can read it. So then I can actually get the information from the parent in the child. So in the child, since it's completely independent, it didn't create anything with howdy child or anything like this, but here when I run it, it should read it if everything is successful. So if I run it, I get print off the child read howdy child. So the parent wrote it to the pipe, and then in the child, it read it from the pipe. Yeah?
I was going to ask, what if it runs the first line in the parent before the child?
Yeah, so the question is, what if the parent runs before the child completely?
First line, like where it closes the pipeline.
So right where it in the child? So if the child executes first and closes the right end of the pipe, remember, after the fork, all the processes are independent. So the child closed its file descriptor, which does not affect the parent. So clone at the time of the fork, independent afterwards. So just because your child closed file descriptor, was that 3? No, 4. Just because the child closed 4 doesn't mean the parent's 4 is closed. Yeah, that's a good thing to keep track of. All right. Any other questions about this? Yeah.
Should we also do the close to the parents?
We'll also have a what, sorry?
Should we also do the close file descriptor?
Ah, that's a good point. So in this case, in the parent, right, I didn't listen to my own advice and close the file descriptors as soon as I know they're not being used. In this case, it didn't matter because I wasn't blocking on anything. I just wrote and then terminated the process and they all got closed. But if I heeded my own advice, the parent does not use the read end of the pipe, so I should close it immediately. And then after I am done writing, I should close the right end of the pipe. So this would be the safe way to write this and the recommended way that you should write this. But I can see it doesn't affect anything. If I run it, it does the same things. All right, any questions about that? Okay, I'll show you some other weird stuff, but for now, here's another fun thing. Okay, let's go back to APS 105 or whatever, and we write something like this. Hello, world. All right, when I execute, hard question, when I execute this, what happens? Prints hello world, right? So, okay, well, now we know a little bit more. So printf, that writes to file descriptor 1, right? So in the vein of screwing with first years, if you wanted to, you could put that at the beginning of their program. What's that going to do?
Close the standard.
Yeah, close standard output, right? And then if I write to it, I see nothing. This can happen to you in lab 2. You were playing with the file descriptors. So you might change file descriptor 1, which is standard output, then use printf, and then you magically think, like, my program didn't make it to that point. But if you close file descriptor 1 and then call print, nothing happens. Because guess what? Did I check for errors from printf? No. Can printf fail? Yeah. So if you want to make something impossible to debug for first years, close 1 at the beginning. And especially if they haven't taken this course, how the hell are they going to fix it? Other than deleting that line. But tell them that, like, it makes their program run faster or something. They don't know anything. All right. Other things. All right. Any other questions about this fun program before I make it more challenging for you? All right. Well, let's see what we have understood. Let's see. Explain what happens when I run this now. I just added a fork. One little simple line. Can't hurt anything, right? And yeah, this is like the kind of stuff you'd have to explain to me and obviously explain on an exam or something like that. So how closely did you pay attention? What will happen? Yeah.
You want to write howdy child twice to the right-hand side?
Yeah, so what should happen is, well, I fork in the parent. It creates another child. I don't differentiate between them, so they're exact copies of one another. They would both do the same thing, and they would both eventually just write hello child. So that pipe would have 2 hello child or howdy childs. Again, don't know why I'm Texan, but 2 howdy childs in it, and then the parent, the child, since it reads over and over again, it should read howdy child twice, right? Everyone okay with that? Yeah. All right, well. Aren't I the best? Yeah.
Let's print howdy child 4 times.
Print howdy child 4 times. Why would that be?
Because that process that, since you're forking within the child process, that code is pretty much going to run twice. It's going to run once in 2 different processes and do the same thing.
So it's going to run twice in 2 different processes. If running one reads hello child, the other one should read howdy child too. So it should get 4 howdy childs. So this is why this course is great. Even weirder stuff happened. I got 2 howdy childs, but they were all read by the same process. If I run it again, there. Sometimes I see 2 howdy childs, but still only 2. I still only see 2. So why is that? Yeah. No, that's you. Yeah.
Because they're identical, so they're reading from the
Yeah, so like the file descriptor like points to a file, right? So if both of them are reading, it uses that same one, and it'll just read all the data and read it once. So across all of the read calls, no matter how many processes there are, we'll get only 2, right? So the reason why we get 2 again is because they all share. There's only 2 things get written to the pipe, and if I read, it doesn't backtrack or anything, it just keeps on advancing. So the reason why I get different output is because I just got unlucky. I have 2 children that are trying to read. I don't know what order they execute in. What could have happened here is that one child read howdy child, like it got the first half, and then the next one executed and it read the second half. Or this could have came from the same process. The same child could have read twice. Or in this case, one process, both writes happened. So in that pipe, there was 2 howdy childs, and then one just called read and then read everything. So because they all happen in different orders, we don't know what exactly the output is going to be. All we know for sure is that if we write 2 howdy childs into it, we will get 2 out of it. And, all right, what happens now? Fork. I mean, it should be the same thing, right? It should just write 4 howdy childs to it, and then I have 2 children that are reading from it. I have no idea what the order is going to be. Oops, I have to compile it first. No idea what the order could be, but I know for sure I'll get 4. So probably every time I run this now, it'll look slightly different. Yeah, every time I run this, it looks slightly different. That has to just do with the order of the operations between the 2. Between processes, you don't know what's going to run, which, yeah, now I know that some of you in 297, you guys had to use threads, right? And they just told you, like, yeah, try not to do things, bad things might happen. That's like different order every time. That's basically threads in a nutshell, and they didn't tell you how to use them properly. So it's just a whole disaster because you can't really explain that or depend on anything. So don't worry, by the end of this course, you'll be able to use threads properly. I don't know why they threw you to the wolves. That's not good, but yeah. All right, so that's about it, unless you want me to do anything else fun with this, but I think we threw enough forks into it. Kind of got the idea. All right, I'll hang around a bit, but just remember, pulling for you.